So if we want to move things up to quadratic, again back to college algebra for a moment. If we have x squared minus 2x minus 15 equals 0. I know I have multiple approaches I can take to this equation, but the most direct one is always to factor the polynomial if possible. Now I know that everything in the real world doesn't factor, and so I have the quadratic formula option if I need it. I do try to stick with things that factor in our book, but I know the author does present some problems that need the quadratic formula. So if I can factor whatever I'm given, I can set each factor equal to 0 and then solve for x. We're going to be very literal here in this step. Set each factor equal to 0, and that leads me to my solutions. Okay, now of course in chapter 2 the problems that we're working with are not going to be x squared minus 2x minus 15. They're going to involve sines and cosines. So we'll do what we just wrapped up with, and initially we'll solve for that sine x or that tangent x or whatever trig function is involved in that equation. And then we'll go back and figure out what angles make that equation true. So maybe I have to pick which one I want to start with. And maybe we'll start with something like secant squared x minus 1 equals 0. If we have secant squared x minus 1 equals 0, and a 0 on the right side, a squared term on the left, so this is not a polynomial. Polynomials don't have sines and cosines in them. But it's a polynomial form, so I can treat it the same kind of way. I say, well, this is a difference of two squares, so I can get it factored on my page. And once I get it factored on my page, I can set each factor equal to 0. And then I can solve those equations for, in our case, for secant x. So if secant x plus 1 equals 0, then secant x equals negative 1. Or over here on the other one, it says secant of x equals positive 1. If you don't like thinking about things in secants and cosecants, then remember you can write them as sines and cosines. And so secant is 1 over the cosine of the angle, which means if I take the reciprocal of negative 1, I still have negative 1. And if I take the reciprocal of positive 1, I still have positive 1. So if I want to determine when the cosine of x equals negative 1, there's only one place there between 0 and 2 pi. We start at cosine of 0 is equal to 1, which means straight across at pi, cosine is negative 1. We just said cosine of x equals 1 when x equals 0. Okay, so there's only one solution to cosine x equals negative 1 and only one to cosine x equals positive 1 in the interval from 0 to 2 pi. Now I know that because cosine has a period of 2 pi, that if I add or subtract a multiple of 2 pi, to my values, that I will have more solutions to that. On this particular guy, maybe I can show you by writing it out instead of doing math in the air. Notice that these guys on the right, these give me all the even multiples of pi. 2, 4, 6, 8, 10, 12, negative 2, 4, 6, 8, 10, 12 pi. On the left side, 2n plus 1 is always going to be an odd number. If n equals 0, we have 1. If n is 1, we have 3. N is 2, we have 5. So on down the line, or negative 1, negative 3, negative 5. So if you were to look this one up in the back of the book, it would say, we're just looking at all of the multiples of pi. Because our right side in the green gives us all the even multiples, The left side in the red gives us all the odds. So we're just saying 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi, or all of their negatives. So we factor if possible, set the factors to 0, solve for x. I've lost my next one. Maybe I have 2 sine squared x plus 3 sine x plus 1 equals 0. And not an actual official polynomial because of the signs in there, but in polynomial form. Okay, I've got a u squared term, I've got a u term in the middle, and I've got a constant at the end. So again, my thought is that I'm going to want to factor this if I can get it factored. If I can't figure out how to factor it, or I'm not convinced that it does, I can use the quadratic formula, as long as I'm careful. If I need to set this problem up as a grouping problem, the 2 factors of 2 that add to be 3 are positive 2 and positive 1. And then I could factor by grouping if I needed to. So I'm going to put some dot dot dots here and say, well, we decided and figured out that this is the product of 2 sine x plus 1 times sine x plus 1. All right, and on any of these, when we get to this step, if you want to hit pause, set the factors to 0, solve for x, see what you end up with, please do that. All right, so you've either unpaused it or just kept watching. I'm going to be literal here. All right, so if we have 2 sine x plus 1 is 0, that tells us sine x is negative 1/2. And we did a very similar one earlier. We said the sine function is 1/2 at pi over 6. It's negative 1/2 in the third and fourth quadrants. So that's 7 pi over 6 and 11 pi over 6. We know because of the period that if we add or subtract a multiple of 2 pi to that, those will also be solutions. Okay, so these are the infinite number of solutions to that equation just from the first factor. If we set the other factor equal to 0, this has fewer solutions, still an infinite number, but fewer on the list. The sine function is negative 1 at 3 pi over 2. Again, because of the period, we can add or subtract any multiple of 2 pi to that 3 pi over 2 and be to more solutions. So lots and lots of solutions to this equation. I'm going to shut this video off with this one. We are going to get to factor some more, but I'm going to, no, never mind. We are, let me argue with myself for just a moment. Yep, we're going to save the last 3 examples, put them on their own video, so we can keep these kind of short.